In the two previous episodes, we talked about the concept and the hardware for a do-it-yourself RF measurement device. In this episode, we will explain the software. Let's recap briefly the status. In the previous episodes, we covered everything from the basic idea to the concept and the hardware realization of our little device. We understand the principle and the function of all components for our project now. In short live demonstrations, we were already playing a bit with the hardware features. And we were showing some interesting applications for the device. It detects and measures practically all radio signals in the frequency range from 1 MHz to 8 GHz. We saw all the elements in action that are in the block diagram. Be it the controls and the LED displays on the front panel, or be it the analog inputs on the backside of the device. However, so far we didn't talk about the software. I mean the Arduino code, which brings the little device to life. In the two following episodes, we want to explain the software. The Arduino code controls the standalone features like the LED displays or the peak hold function on one hand. On the other hand, it performs some data pre-processing and it controls the interface to a PC in both directions. Since we have more than 1000 lines of code, we need to talk about the software structure first. Then, instead of killing you with an endless software requirements list, I want to demonstrate some features that we can use with a PC and a terminal program. This gives us an immediate impression of the features. We will see the details later on, when we talk through the code. The part 1 will cover the setup and the main program. There will be a part 2 which covers the rest of the software plus additional examples. The Arduino code is built according to the usual standard represented by the green boxes here. It is using a main program loop, definitions, settings and functions called voids. And somehow we need to realize a number of functions that I summarized under the topics in the blue boxes. And then we need to take care that the little monster lurking at the bottom doesn't mess up everything. I'm not the greatest programmer, however, I tried to give the software a proper structure. This helps a lot to stay on top of things when you need to debug, change or extend the code. But it happens always, you know, as soon as you finish the project, you can still see a lot of potential for further improvements. In my case here, I would use even more voids to keep the main program a bit cleaner. Another tip that I want to give is to follow a strict naming convention for the variables that you use. This helps your own understanding of the code, especially in case you want to reuse parts for other projects. The complete Arduino code for this project is provided in the download section. The demos so far were showing us how to use the device in the standalone mode. We just had to power it using a USB charger or a power bank. As promised, we will now demonstrate the interaction with a PC using CoolTerm, which is a freeware terminal program. Of course, in this case, the device is powered through my PC and it starts immediately to work once the USB cable is plugged in. I'm using an Apple Mac version here, however, you will find also a Windows version for CoolTerm to download. We start CoolTerm and first we need to adjust the right USB port and the speed, which is 38,400 baud. In my case here, I already stored the settings before, so that I just have to load them. Then I just need to push connect and off we go. The help menu from our self-made device is showing up. We can run and stop the data recording by using the R and the S keys of our keyboard. I stop it for the moment. We can see a bunch of data and we always get the current settings of all parameters that we also can adjust through this interface. Using the H key, we always get back to the help menu. We can see here that besides R, S and H, there is more short controls available. Using A, O and T gives us endless comma-separated values, while R gives us text with a defined length. The text option has now plenty of additional settings. We can define the time interval for our measurement records, the number of records, we can adjust a floating average window, the peak hold time for the recordings, and the dBm level to calculate the duty cycle of the signal in the set time interval. And by the way, these values are independent from the ones that you can adjust with the manual controls on the front panels. Then we can define some options for the output columns and the brightness of the LED displays. There is quite a lot of parameters that you can change. But don't worry, when you start the device the next time, it always comes up with the default settings. Now let's see how we can control the parameters. First, we open a serial connection window in CoolTerm. Next, we type in a command that we learned from the help menu. In this case, it is the brightness of the LED displays. We change it from the default 250 to 40, which dims down the LEDs. Please note that you always need the semicolon after each command. After sending this command, we will find under the current settings that the brightness has changed from 250 to 40. Of course, we also realized that the LED displays of the device are dimmed down. We let it run further. Note the headlines here. They only appear in the text mode. and we stop it again. Now we check the other short controls that deliver endless comma-separated values. The key O delivers the RSSI values, T delivers the full set of data, and A delivers just the analog voltages. Here I have another tip. A nice idea is to feed the comma-separated values directly into a telematics program. I will explain this occasionally in another episode. I need to mention that for the Arduino Nano, your PC needs a USB driver. You can get it either by installing the Arduino IDE, or you can download a separate USB driver you can find in the internet. Now let's have a look on the data that we get in the text mode. As a standard, we get a running number in the first column. Then we get a timestamp in seconds. Then we get the voltage on input A1, where we currently connected a solar panel. In the low light, it is giving us only about 2.7 volts. Then we see the voltage on the inputs A2 and A3. Then we get the current RSSI value, the mean RSSI value in the defined averaging interval, and the peak value in the defined interval. The last column gives us the duty cycle in the defined measurement interval. In the parameters, we can set the trigger level in dBm for this. Let's get to the code. First, I need to give an important hint. I only got this working by choosing, of course, the right board, which is Arduino Nano, and then I had to choose the old bootloader. I have always a lot of comments in my code where I documented ideas, problems, solutions, bugs, tests and interesting information which I found. It's not all in English, but I translated the important parts. I also kept the German comments here, just in case you can read it. The actual code starts with the set definitions. We also have to include the Adafruit library for our NeoPixel display. And then we find lots of variables. We need especially a lot of string variables for the data exchange and the control commands that come via the serial interface. In the setup part, we need to initialize the serial interface. And we define the pin mode for some pins that we want to use for the 3 LEDs and the switch. The following voids are sending the help menu and the current parameters to the serial interface. Next, we go to the main program. It needs some counters to control average and peak values. Then we read the analog input values here. The input A0 is used internally to calculate the RSSI values. The inputs A1, A2 and A3 are used to measure voltages. Since the resistances of my voltage divider resistors is not 100% accurate, I did a calibration with the numbers you can see in the formulas. Keep that in mind when you build your own voltage dividers. You can achieve a much better voltage measurement accuracy with that calibration. Next, we compute the RSSI values in dBm. As said earlier, we calculate the current values, the mean values and the peak values over defined intervals. And then we calculate the duty level in intervals. Here we process the input from the potentiometer that controls the gain. And in the next section we find the same for the peak hold time potentiometer. Here is a debug message that we could activate. And then we see the code for the mode switch. We can switch the NeoPixel display between the RSSI and the analog voltages that are coming in red, green and blue on the ring display. The outcommented stuff here you can use in case your NeoPixel ring works the wrong direction. I kept it to remember what we need to change in that case. Next, we check the serial interface and read the information in case there is something available. Then we need to parse the input in order to filter out the control commands. Since we might have changed parameters, we send the current settings to the serial interface. With our short commands, we start the desired output action, which can be the data in the bespoke text format or in the endless comma-separated formats. The outcommented part here is a test function that I used in the beginning to develop the code. We also indicate the current mode by the LEDs that can change the brightness according to a brightness variable. And then we have the actions for the other short commands. They can give us the RSSI values or analog voltage measurements only. Finally, there is the code for the telematic mode that just spits out all the measured values comma separated. Okay, this is the end of the main program loop and our video is already pretty long. Let's make a cut here. The remaining part of the code and some recorded examples will be subject to the next episode, which is part 2. Now stay tuned and don't forget to subscribe and support the channel. See you soon in the coming episodes.